Most engineering teams rely on a familiar metric to feel safe about their code: test coverage. The logic is if coverage goes up, we assume quality goes up too. But here's the uncomfortable reality. Some of the most dangerous bugs don't show up as coverage gaps at all. This paper asks a deeper question. What if we stopped asking what code isn't tested and instead asked what kinds of failures would really hurt us if they slipped through? And then build tests specifically to catch those. The authors of this paper are at Meta, and for them, the stakes are really high. You see, traditional automated testing focuses on structure: lines covered, branches exercised, paths hit. That works up to a point. But real production failures are rarely about unexecuted lines. They're about semantic mistakes, logic that behaves incorrectly under specific conditions, especially around things like privacy, security, and compliance. Teams know these risks exist, and that's the crazy part. They often have incident reports, bug postmortems, or regulatory requirements written in plain language. The hard part is this: how do you turn vague human concerns into concrete unit tests? So, if I had to summarize the core idea in the paper, it is this: generate the bug first. Instead of asking an LLM to directly write tests, first ask it to generate realistic, false, simulated bugs that represent a specific concern. These simulated bugs are called mutants in this paper. They call this system ACH, Automated Compliance Hardener, which uses LLMs to read a textual concern, like a privacy issue seen before, generate a version of the code with a realistic bug that reflects that concern, and then generate a test that could catch that bug. If the test fails on the mutant but passes on the original code, the test is useful. Now, mutation testing is nothing new. Traditionally, tools generate thousands of small, rule-based mutants, and that creates two problems. First, too many mutants to manage, of course, and many of them aren't realistic or even relevant. ACH flips this approach. It generates fewer, highly targeted mutants, guided by real organizational concerns, especially around things like privacy regressions. And crucially, engineers never review the mutants. They only review the tests, just like any other code change. This keeps developer friction low while still targeting high-impact risks. How ACH works? So at a high level, the system does four things. First, it takes free-form text describing a vague concern, for example, patterns from past privacy bugs. Second, the LLM generates simulated faults in relevant code. Next, another LLM agent filters out equivalent mutants, cases where the code looks different but behaves the same, using a mix of model judgment and simple static rules. Finally, a test generation LLM writes unit tests that specifically kill the remaining mutants. Only tests that build, pass reliably, and catch previously undetected faults are proposed to engineers. And here's what happened in production at Meta when they deployed ACH. By the way, they deployed it across apparently 7 major Meta platforms, including WhatsApp and Messenger. The results are striking. Over 10,000 classes analyzed, 571 new tests generated, 73% rate by engineers, where only 1/3 of accepted tests were strictly privacy related. Yet, engineers still accepted many others because they added real value. Perhaps most importantly, though, nearly half of the tests that caught real faults did not increase line coverage at all. They would have been missed by line coverage only strategies. For leaders, this paper reframes how to think about testing and AI. That's what I find so exciting about this paper. The biggest gains don't come from more tests or more coverage. They come from targeting the right risks. LLMs are most powerful when they translate human concerns into concrete artifacts. We've seen this. And work inside existing review workflows. The takeaway here is super simple. Good testing isn't about more code coverage. It's about protecting what matters. Check out the school paper in the description box below, and thank you so much for watching.